Welcome to this explainer. Today we are going to uncover the invisible mechanics that are actually holding modern AI back, and then we'll look at a brilliant new architecture designed to totally fix it. If you've ever been amazed by a large language model's vast knowledge, but then completely baffled by its inability to do something simple, well, you are definitely in the right place.
So let's dive into this crazy paradox. How can an AI write a perfectly structured, incredibly sophisticated sonnet, but then utterly fail at spelling a basic word, or counting the letter R in a sentence, or just doing simple arithmetic? It kind of feels like a glitch in the matrix, right? Well, the answer actually lies in this hidden translation layer that sits right between our human prompts and the AI's core brain.
Here's our roadmap to understanding all of this today. First, the tokenization bottleneck. Second, fractured thoughts and modality gaps. Third, the byte-latent transformer. Fourth, dynamic entropy patching explained. And finally, number 5, a tokenizer-free AI future.
All right, starting with section 1, the tokenization bottleneck. Okay, so before a neural network can even begin to process human language, it essentially forces our continuous associative thoughts through a super narrow bottleneck known as byte pair encoding, or BPE. It's basically a compression algorithm. It scans text and merges frequent adjacent characters into discrete numerical IDs. Think of it like trying to force a beautiful, detailed painting through a pixelated fax machine. The machine literally cannot read our language. It can only read those compressed IDs. So the really crucial takeaway here is that BPE takes our continuous, fluid human thoughts, our highly relational wet code, if you will, and forces it into the discrete, rigid, binary, dry code of machine tokens. And this is a perfect example of the severe logical vulnerabilities that creates. Because BPE operates purely on character frequencies in its training data, the word good with a lowercase g and the word good with a capital G actually get assigned completely distinct internal IDs. No way, right? The model literally has to burn its internal computational capacity just to figure out that they mean the exact same thing. And it gets worse with math. The constant 3.14155 might get arbitrarily chunked by the tokenizer into a 3, a decimal point, a 14, and a 159. Because these arbitrary boundaries don't align with systematic decimal logic at all, the AI simply cannot learn systematic arithmetic. It's really just memorizing arbitrary strings of numbers. Moving on to section 2, fractured thoughts, modality gaps.
Noam Chomsky actually points out a massive vulnerability here. He notes that while the human mind naturally seeks to create continuous logical explanations, LLMs that are bottlenecked by these tokenizers operate purely as probabilistic pattern matchers. They're just inferring brute correlations between discrete tokens. This massive disconnect between true semantic meaning and brute force token prediction creates what researchers call a modality gap.
And this modality gap isn't just some abstract theory. It has devastating real-world symptoms. First up is multilingual fragmentation. Languages like Khmer or Arabic suffer up to a 15 times token inflation that wastes compute and severely degrades performance. Second, we see visual reasoning collapse. If you feed an AI a screenshot of text instead of pure text tokens, its step-by-step logic completely collapses, generating answers that are up to 19 times shorter. And finally, these models completely lack orthographic knowledge. They literally don't know how words are spelled because they never actually see the letters. They only ever see those compressed token IDs.
Which brings us to section 3, the byte-latent transformer.
Okay, this is where things get genuinely exciting. Enter the byte-latent transformer, or BLT for short. This is an absolute paradigm shift. Instead of relying on a static, pre-calculated subword vocabulary like BPE, the BLT operates directly on raw, uncompressed byte sequences. By completely ditching that rigid dictionary, the model interacts directly with the raw data of the world. It operates much, much closer to how information actually exists in reality.
You can think of the BLT architecture as this highly efficient, intelligent assembly line. Step 1 is the local encoder, which dynamically groups raw bytes into flexible patches to capture context. Step 2 is the global transformer. This is the powerhouse that processes these concepts step by step. And finally, step 3 is the local decoder, which flawlessly unpacks those global predictions back into exact raw byte sequences. It is just incredibly elegant.
Let's look closer at that in section 4. Dynamic entropy explained.
Now you might be wondering, how does this system actually know where to group these bytes without a predetermined dictionary telling it what a word is? Well, let's dive into this ingenious mechanism called entropy patching. See, traditional tokenizers force a model to spend the exact same amount of compute on every single token, whether it's just the highly predictable end of a common word or the complex beginning of a brand new thought. BLT completely changes this by using a data-driven approach based on entropy, which is just a mathematical measure of uncertainty. Basically, a small, hyper-efficient byte-level language model calculates exactly how hard it is to predict the next byte.
This approach essentially acts like a really smart manager. When the incoming data is highly predictable, like say everyday language or the end of a common word, the entropy is low. So the system groups this into long patches, breezing efficiently through the text and saving massive amounts of compute. But when the data is complex, uncertain, or noisy, like numbers, code, or a rare word, the entropy spikes. The system immediately creates a boundary, generating short patches to apply maximum computational attention exactly where it is needed most.
And finally, Section 5, a tokenizer-free AI future. So, does this fluid, dynamic approach actually hold up against the traditional rigid system in practice? Absolutely. The hard data here is just fascinating. For years, byte-level models were considered way too computationally expensive to scale up. But as we can see, the BLT, through its dynamic entropy patching, successfully matches the performance of standard tokenization-based models like Llama 2 and Llama 3, even at a massive 8 billion parameter scale.
But here is the truly staggering takeaway. It achieves that matching performance while using up to 50% less computational power during inference. I mean, let that sink in for a second. By intelligently allocating its resources, it's not just fundamentally better at understanding the data, it is vastly cheaper to run.
So by removing the tokenization bottleneck, we effectively eliminate the modality gap entirely. And the advantages are literally a game-changing leap forward. We get absolute zero out-of-vocabulary errors, meaning any sequence of text, emoji, or code can be seamlessly parsed. We restore equity for multilingual text, so non-Latin script are no longer unfairly penalized by bloated token counts. The model becomes extremely robust to typos and noisy inputs because it's actually reading the characters. And it paves the way for handling diverse data modalities seamlessly, treating information as a fluid signal rather than just a rigid dictionary lookup.
Which leaves us here. We've seen how trying to eradicate the natural ambiguity of human language by forcing it into rigid, discrete, dry code actually fractures an AI's ability to reason. The byte-latent transformer proves that embracing the continuous fluid nature of raw bytes isn't just possible, it's wildly efficient. So I'll leave you to chew on this final thought. Is the very messiness and continuous nature of human data not a bug to be compressed away, but actually the ultimate vital feature our AI needs to unlock true reasoning? Thank you so much for joining me on this explainer, and keep exploring.